So today on Test Case TV, we're actually going to go from using a single LED and a single resistor to using multiple LEDs and one resistor, but we need to figure out how to plan accordingly. And in order to do that, we're actually going to discuss two really fundamental concepts for planning out your circuits. One is putting components in series, and the other one is putting components in parallel. And we'll discuss what that means here in a second. When we start discussing parallel, what we're actually going to be discussing is having components that have equal access to ground, power, data, but if I remove one of those, it does not affect the circuit. Whereas when we discuss series, we're talking about a dependency of one component transmitting power through it so the other one can then have access. So if we pull an LED out of that system, all the lights go off. But in the parallel system, you pull one out and they all stay on, except for the one we pulled out, obviously. So with this being said, we're going to start planning out our system, right? So let's pull the 5-volt line like we did before, and we'll use the red LEDs because they have the 1.7 drop that we can count on, and we'll use 3 of them, all right? So 5-volt, red LEDs, 3. Now let's plan our parallel circuit first. And what that's going to mean is that since all 3 LEDs have access to the same power, they're all going to want to pull about 20 milliamps because that was our goal from before. So it's going to be 20 plus 20 plus 20. So we have a 0.06 amp that we want to put in our equation for Ohm's law. So 5 volts minus the 1.7 voltage drop for all these LEDs, so we know we're at that threshold, equals 0.06 R. That's going to give us a 55 ohm number for our resistor, but since we know that we're not pulling exact 55s, I can use a 60 ohm for my circuit and I'll be happy with that. The next thing that we're going to do is the series component. So let's say we have the 5-volt source and we know that there's a forward voltage drop of 1.7 per red LED. So if we have electricity go through the positive, down negative, that feeds the positive side of the next LED down to negative, positive side of a third one down to negative. We do that and there's going to be a 1.7 drop every time. Well, the problem with this is that's going to give us a negative 0.1 volts, which means that our circuit doesn't have enough potential energy, enough available resources to actually light the 3 LEDs. So it's not sufficient. And this is one of those key moments where you will see people choose a higher voltage source to accommodate many components that can pull from it. And that's for a 5-volt series circuit. So since we've seen that the series circuit for 5-volt is not sufficient, let's up the voltage because we can plan for that. The 5-volt source is now going to be 9. And we have the forward voltage of 1.7, 1.7, 1.7, and that's going to give us about 3.9 volts to play with, and that's where we chose our resistor. Now that we have a circuit that can complete, since they're all going through the 3 LEDs, we're only pulling 20 milliamps because they're all getting the 20 milliamps current, and that's going to make them all happy, and that's what we're planning for. So in doing the series with the 9-volt, that's going to leave us at a 3.9 voltage equals 0.02 amps. Is going to give us a 195 ohm resistor. And since 195 isn't something you're going to find, a 200 will work just fine. So that's going to be our happy circuit for 9-volt, which is higher power source, but depending on the voltage drop for those LEDs. So if we plan out our circuit for the 9-volt source and 3 LEDs in parallel, there's going to be a couple things that happen. Like one, we still know that the parallel circuit for LEDs is going to be 0.02 plus 0.02 plus 0.02 on the 9-volt line, right? Now we also have to account for the voltage drop, so all LEDs can hit that threshold to be happy, and that's going to be the 1.7. So now we have 9 volts minus 1.7, so that's our 7.3 is going to be equal to now 0.06 times R. That's going to bring us to our resistor value of about 120 ohms. So that all makes sense, except for this new thing called wattage. You may be aware of it, you may not, but it's something we now need to take care of because we're pulling more power through our circuit. And that means that our resistor is actually going to be having to dissipate more energy in the form of heat. That's going to make us be more aware of the overall energy going through our system. And we calculate this with wattage. So watts equals current times voltage. Now in this case, we're dealing with 7.3 volts times the 0.06 amps. And that's going to be well over our 0.25 tolerance for a quarter watt resistor, which means that resistor is going to burn out. So now we found out why people might choose to increase their voltage to accommodate a series circuit, but now in parallel we're setting up a situation which is possibly detrimental to what we're actually trying to accomplish. So finding a balance between when to choose parallel versus series, or finding a way to make combinations of the both, is really what is going to help you leverage really amazing stuff moving forward. So I hope this is a really good introduction to these things. If there's any questions, as always, you can ask below. And enjoy, have fun making, and we're going to move on to the next thing. All right.